Hello everyone, welcome back to another video. Today we're going to take a look at the KZN September 2025 paper 1 questions. Question 1.1. A physics learner stands on a scale in a lift that is moving upward at constant velocity. So constant velocity means that acceleration is equal to 0, and that means that F net will equal 0. The reading on the scale compared to the reading when the lift was stationary would be the same. So the answer is D. Because there is no F net, the reading on the scale is going to be the same. Question 1.2. Two blocks of masses m1 and m2 are connected to each other by a light inextensible string. The blocks are accelerated upward by a force F. The tension in the string between the blocks will be, so will it be equal to F? They don't tell us that it's moving at constant velocity, so that seems unlikely. Equal to m2g, less than m2g, or greater than m2g. So let's draw a free body diagram for the mass 2. So mass 2 is going to experience the tension, so tension going up. It's also going to experience the force of gravity pulling it down. Now, because acceleration is upward, I'm choosing up as positive. F net is going to equal ma. I'm going to say that tension minus Fg is going to equal ma. That means tension is going to equal ma plus Fg. Now we can rewrite that a bit. We can say tension is equal to m2a plus m2g. So the answer here is going to be D, because the tension is more than m2g. Question 1.3. A ball is dropped from a height h and hits the ground with a speed v. The speed of the ball at the moment when it reaches half its initial height is. So let's work this out. So since it is dropped, the vi is equal to 0. And we can then use a shortcut. And the shortcut is, if an object is dropped from rest, we can calculate its velocity at any point during its motion by using the formula v is equal to the square root of 2gh. Now there's a few ways we can derive this formula, but that is the formula. So if this is my original formula, as we can see, h, it's dropped from a height h, v, its velocity when it hits the ground is v, so let that be my original formula. So v halfway through, so let's call that v half, is going to equal the square root of 2 times g times half h, because remember we want the velocity halfway through the fall. We can simplify a bit inside this or under this hood. So half times 2 is 1, so this is simply going to be the square root of gh. Now what we can do is we can rewrite this, and I can write it as v is equal to the square root of 2 times the square root of gh. But we know, or we just worked out, that the velocity halfway through is equal to the square root of gh. So let's replace that. So v is equal to square root of 2 times v halfway through the fall. Let's rearrange. So v halfway through the fall is going to be v divided by square root 2. So the answer there is B. Let's take a look at question 1.4. A trolley with a mass m has momentum p. The kinetic energy of the trolley will be. So what we need to do here is to say P is equal to m times v. Now V is therefore going to equal P divided by M. But they want kinetic energy, and kinetic energy is equal to half mv squared. So let's work on getting v squared. So I'll square this side, and then I'll have to square this side. So v squared is going to equal p squared divided by m squared. Now we need the m. So let's multiply both sides by m. So this m will cancel with that. I'm going to have mv squared is equal to p squared over m. Now we need the half. So I'm going to divide both sides by 2. And I'll divide this by 2. So ek is equal to p squared over 2m. That answer is D. Question 1.5. An object is moved from rest in a straight line across a flat surface by a changing horizontal force. The changing force is plotted against the position of the object to produce the graph below. The work done on the object by the applied force from x equals 0 to x equals 8 is. Now we can use the formula. Work is equal to F times delta x times cos theta. Now F times delta x is actually the area. So if I want the work, I just calculate the area under this. So area is going to equal half base times height, and that's equal to 40 joules. So the answer is A. Question 1.6. The reason why the observed pitch of sound wave of an ambulance decreases as the ambulance moves away from a stationary observer is. So the frequency is decreasing, but we know that V is equal to F times lambda. Since V is constant, if F decreases, it means that lambda is going to increase. So the answer to 1.6 is C. Question 1.7. Point charges with magnitude Q, 2Q, 3Q, and 4Q are placed in different electric fields. The force on each point charge is measured, and the results are recorded in the table shown below. Which point charge experiences the greatest electric field strength? So to calculate electric field strength, E is equal to F divided by Q. So all we need to do is go through each option, divide the force by the charge. So for example, we'll start with A. We'll say 60 divided by, and just take the value or the coefficient. So 60 divided by 4, that's going to give you 15. Then you check B. You'll do 20 divided by 1, which is 20. You check C, you get 25 divided by 2, which is 12.5. Then D is 33 divided by 3, which is 11. We're looking for the greatest electric field, so the answer is going to be B. Question 1.8. Two identical light bulbs, P and Q, are connected as shown in the circuit diagram below. The internal resistance of the battery can be ignored. When switch S is closed, which combination best represents the effect on the ammeter and the brightness of the bulb? So these two bulbs are connected in, or when the switch is closed rather, they will be connected in parallel. So if you add a resistor in parallel, the total resistance decreases, which means that the current will increase. So we have option A and option D. Now we need to consider the brightness of the bulb. And to do that, let's take a look at the diagrams. So if I have a circuit, and that circuit has a resistor with a resistance of X, the total resistance is going to be X, and let's say the total current, let's call that Y. But if I add a resistor in parallel, and those two resistors have the same resistance, X and X. The total resistance now is going to be half X. But because resistance and current are inversely proportional if voltage is the same, my total current is now going to be 2Y. So 2Y is going to be flowing through here. But when it gets to this branch, it's going to split. You're going to have Y and Y, whatever the value is. So what we notice is the current going through each is going to be the same as it was before. So because the current is the same, it means that the brightness is going to be the same. So the answer is A. Question 1.9. The diagram below shows a coil in a magnetic field. When the coil is part of a DC motor, which one of the following must be connected to X and Y? The answer is A, a split ring commutator. Question 1.10. High energy light is shone onto a metal plate. Electrons are emitted from the metal plate. Which combination will be true when the wavelength of the light is decreased? So C is equal to F times lambda, the speed of light. If I decrease the wavelength, it's going to cause the frequency to increase. If the frequency increases, that's going to cause the kinetic energy to increase. So the options we have are B and C. But the number of emitted electrons are not going to change. Only intensity of the light affects that. So the answer is going to be C. Question number 2 reads, a block X of mass 6 kilograms at rest on a horizontal rough surface is connected to another block Y of mass 3 kilograms by means of a light inextensible string which passes over a frictionless pulley. A force of 50 newtons is applied horizontally to block X as shown in the diagram below. The coefficient of kinetic friction between the horizontal surface and block X is 0.3, and there is no friction between the surfaces of blocks X and Y. Question 2.1. Draw a labeled free body diagram showing all of the horizontal forces acting on block X. So block X is going to experience a force applied to the left. It's going to experience a force of tension to the right. And because they tell us about friction, well, kinetic friction, it means that it's also going to experience friction going to the right because it's being pulled to the left. Now, question 2.3.1. Calculate the magnitude of the frictional force acting on the block. So friction is equal to mu k times Fn. Mu k has been given to us as 0.3, but Fn is not necessarily going to be Fg every single time. Let's take a look at this example. If we draw a free body diagram for X, X is going to experience a force of gravity going down. It's also going to experience the normal force going up. And this is for most cases. But because Y is on X, there's going to be a force downward. That's going to be the force of Y on X. So the normal force is going to be the sum of these two forces. So it's going to be Fg, which is mass times gravity. So 6 times 9.8. And then plus the force of Y on X. Y is pushing its entire weight down on X. So the force of Y on X is going to be its weight. So it's going to be 3 times 9.8. And that gives us a friction value of 26.46 newtons. Question 2.3.2 says calculate the acceleration of each block. Now to answer this question, we need to look at the free body diagram for object Y. So for Y, it's going to be just simply three forces. You're going to have the weight so Fg, you're going to have the normal force going up. You're also going to have the force of X on Y, and you're also going to have the tension. The tension is pulling it to the right. And this is for the 3 kilogram block. Now, we need to apply F net equals MA to both blocks. Because it's worth 6 marks, we need to use simultaneous equations. So the free body diagram I've drawn at the top is going to be for the 6 kilogram block, and the one at the bottom is going to be for the 3 kilogram block. However, because these blocks are connected to a string, and because of the situation that they are in currently, both the blocks are not going to accelerate in the same direction. So the 6 kilogram block is actually going to move to the left, whilst the 3 kilogram block is going to move to the right. So for each block, I'm going to have a different direction as positive. Now this is kind of like the situation where you have a table and you have something at the top, you have them connected with a rope, and if it's being pulled to the left, you have 2 different directions as positive. For one, you'll have up as positive, the other you'll have left as positive. So for the 3 kilogram block, I'm going to choose right as positive, and for the 6 kilogram block, I'm going to choose left as positive. So for the 6 kilogram, I'm going to have F net equal MA. So I'm going to have FA minus friction minus tension equals MA. The force applied was 15 newtons minus the friction 26.46 minus tension is equal to 6A. Let's simplify a bit. We are going to get 50 minus 26.46 is 23.54. So 23.54 minus 6A equals T. Now for the 3 kilogram block, I'm going to go F net equal MA. Now remember, for the 3 kilogram block, right is positive. So it's just going to be tension. So tension is going to equal 3A. Now I can equate the tension because it's the same rope. So I'll say 1 equals 2. That means 23.54 minus 6A equals 3A. I can take this over. So 23.54 equals 9A. That means A is equal to 2.62 meters per second squared. So that means for the 6 kilogram block is going to accelerate to the left, whereas the 3 kilogram block is going to accelerate to the right. M weighs half his weight compared to his weight on the surface of the Earth. The mass of planet M is twice that of Earth. 2.4.2, calculate the radius of planet M in terms of the radius of Earth. So from this first part here, if his weight is half, remember Fg is weight, and that's equal to mass times gravity. If the mass is constant, it means that the weight is going to be proportional to gravity. So if the weight is half, it means that the gravity must be half. So now we can set up some kind of equation. So in other words, if I halve the gravity on Earth, I'm going to get the gravity on planet M. But to work out the gravity on Earth, so half is going to be GME, so the mass of Earth, divided by the radius of Earth squared. And that's going to equal capital G, and the mass of planet M is 2 times the mass of Earth. So I'm going to put 2ME divided by, and we don't know its radius, so let's call that x, so x squared. Now let's simplify. So I can cancel G from here, G from here. I can cancel ME from here and ME from there. I'm going to be left with half times 1 over RE squared is equal to 2 over x squared. Now I can combine this. I can say 1 over 2RE squared is equal to 2 over x squared. I can switch these now. I'll get x squared is equal to 2 times 2RE squared is 4RE squared. That means x, square root both sides, you're going to get 2RE. It's going to be double the radius of Earth. Question number 3. A ball of mass 500 grams is projected vertically downward toward the ground from a height of 2 meters at a velocity of 1.5 meters per second. The position time graph for the motion of the ball is shown below. Now, this graph looks really hectic, so I think it's just there to throw us off. So I'm just going to draw a diagram just so that we can understand what's going on here. So here's the building or whatever the case is, and that's 2 meters. Then you have a ball and it's thrown down, and its initial velocity is 1.5 meters per second, and it's going downward. And we can see that there is a gap here, meaning that's going to be contact time. And also we can see that the ball is bouncing. So it hits the ground, it bounces, it reaches a certain height, and it bounces again and it reaches a certain height. So this is actually going to be the first bounce, and that's going to be the second bounce. The question 3.1 says, write down the maximum vertical height reached by the ball after the second bounce. So after the second bounce, the ball reaches a height of, we won't say minus 0.6 meters. Instead, we will say 0.6 meters. So it reaches a height of 0.6 meters. Question 3.2.1. Calculate the speed with which the ball hits the ground for the first time. Now, because the ball is moving downward, I'm going to choose down as positive. So I'm going to represent it like this. So that's telling the examiner that I've chosen down as positive. Now the quantities I know VI is going to be positive 1.5. I know acceleration is going to be positive 9.8. And I know the displacement of the ball is going to be 2 meters. And that's all going to be positive because it's moving downward. So if they want to know what is the speed, they want to know what is VF. So I can use the equation VF squared is equal to VI squared plus 2A delta Y. You can write delta X if you want. Delta Y is just a different form of the equation because it's moving in the Y axis. So 1.5 squared plus 2 times 9.8 times 2 meters. We can simplify. We'll get 41.45. Now to get VF, we need to square root this. So the square root is going to be 6.44 meters per second. We don't need to put a direction because speed, which they are asking for, is a scalar quantity. Now question 3.2.2 reads, calculate the time t1 indicated on the graph. So t1 is the time that it takes to hit the ground. So if we know all of these quantities, we can use the first equation to calculate the time. So once again, I'm going to keep down as positive. So VF is equal to VI plus A delta T. So 6.44 is equal to 1.5 plus 9.8 times delta T. We can then simplify, take the 1.5 across. You'll get 4.94 is equal to 9.8 delta T. Delta T is therefore going to equal 0.50 seconds. Question 3.2.3. Calculate the velocity with which the ball rebounds from the ground during the first bounce. So when it rebounds, it's going to be moving in an upward direction. So though it is not advisable to do this, I'm going to do it anyway, just because it's simpler. I'm going to choose up as positive, because the answer that I'm expecting is going to be a positive answer now. It just makes it easier to work with. Now, if I'm choosing up as positive, what are the quantities that I would know? So I know that the acceleration now will be minus 9.8. The ball is rebounding, it's traveling upward. So its displacement is going to be positive because I've chosen up as positive. So delta y is going to equal, so how high is the ball going to travel on the first bounce? It's going to travel 0.8 meters. And at that 0.8 meter mark, it stops. So I know its VF is 0. So I want to know what is the velocity at the start of that motion. So I want to know what is VI. So again, I can use the formula VF squared is equal to VI squared plus 2a delta y. So 0 is equal to VI squared plus 2 times minus 9.8 delta y 0.8. We can then simplify and take it across. We'll get 15.68 is equal to VI squared. VI is equal to the square root of 15.68, which is 3.96 meters per second. And it's upward. The next part says the ball is in contact with the ground for 0.2 seconds during the first bounce. Question 3.3, calculate the force exerted by the ground on the ball during the first bounce. So F net times delta t is equal to delta p. Now I'm going to choose up as positive because I want the force that the ground is exerting on the ball to be positive, because the ground is going to push the ball upward. So F net times 0.2 is going to equal 0.5 into, on rebound, the ball is moving 3.96 up, so that's going to be positive 3.96 minus, and then on the way down, the ball hit the ground with a velocity of 6.44 meters per second downward. And since I've chosen up as positive, it needs to be minus 6.44. And that gives us an F net of 26 newtons. But that's not the answer, because if we draw a free body diagram of the forces acting on the ball when it's in contact, the ball is going to experience a force of gravity, and it's going to experience the force of the ground on the ball. Right? So, since I've chosen up as positive, I can say that the force of the ground on the ball, so ground on ball, minus Fg, so minus 0.5 times 9.8 is equal to 26. That means the force of the ground on the ball is going to equal 26 plus 0.5 times 9.8, which gives us an answer of 30.9 newtons upward. Question 4 of the paper says a boy of mass 60 kilograms on ice skates is stationary on a frictionless surface. He throws an object of mass 4 kilograms at 3 meters per second horizontally in a westerly direction as shown in the diagram below. At the instant the object leaves the boy's hand, the boy starts moving. Ignore friction. Question 4.1, in which direction does the boy move? Right only, east or west? So if the object is going to move to the west, it means that the boy is going to move to the east, right? Question 4.2, name and state the law which explains the direction in which the boy experiences a force when he throws the object. So this is going to be Newton's third law. Newton 3. Basically, when an object exerts a force, when object A exerts a force on object B, then object B will simultaneously exert a force on object A. And the force is going to be of an equal magnitude, but in a different direction. Or thereabouts. As close as I can remember. Question 4.3. Calculate the speed of the boy immediately after the object leaves his hand. Now this is a momentum question, and so we can use momentum to solve this. We can say that the sum of the momentum before the inverted commas collision is going to equal the sum of the momentum after the collision, inverted commas. Now, because the object and the boy and this whole system isn't moving before the collision takes place, the momentum is 0. And that's equal to, now I'm going to choose left or west as positive here. And so once the boy throws it, they move as independent objects. So it's going to be the mass of the object times the velocity of the object plus the mass of the boy times the velocity of the boy. So 0 is equal to, the mass of the object is 4, the velocity of the object is going to be 3, plus the boy is 60, and the velocity is VB. Now we can solve for VB. The velocity of the boy is going to equal minus 0.2 meters per second. But the question asks for speed, and so we shouldn't leave it as a negative. We should just instead just say that the velocity of the boy is going to be 0.2 meters per second. Question 4.4, or 4.4.1. How will the answer in 4.3 be affected if the boy throws the object at a higher velocity? Choose increase, decrease, or remain the same. Yeah, we don't need to overcomplicate it. Just imagine that you increase the value. So you can say 0 is equal to 4 times, let's make it 5, and then plus 60 times VB. When you solve for VB, that's going to equal 60 divided by negative 20, which is equal to negative 3 meters per second. You can see that it's increased. So the answer is going to be increase. Question 4.4.2, if they increase the mass or they double the mass, what's going to happen? Well, similarly, it's going to increase the momentum of the object, and so it's going to affect the velocity of the boy. So it's going to increase as well. Now, question 4.4.3 asks us to explain this. So if you increase the mass, right, that's going to increase the momentum of the object. And that's going to also increase the momentum of the boy, because the momentum before is equal to 0. And that's going to cause the velocity of the boy to also increase. Now, you can make the argument, or you could use this other explanation that says that the change in the momentum of the object is going to increase, right? And therefore that's going to cause the change in the momentum, so this is or the change in the momentum of the boy to increase as well. Taking a look at question 5, a box of mass 7 kilograms, which is initially at rest, is acted upon by a constant force of 18 newtons that is applied at an angle of theta to the horizontal. The box experiences a constant frictional force of 8 newtons as it moves from rest at point X along a horizontal surface to point Y and passes point Y with a speed of 1.5 meters per second. Question 5.1. Draw a labeled free body diagram showing all the forces acting on the box as it moves. So 5.1, here's the block. It's going to experience a force applied at an angle. It's going to experience the force of gravity. It's going to experience a normal force. And it's going to experience friction. Question 5.3. Calculate the size of angle theta by using energy principles only. So I'm going to use W net is equal to delta EK. Now FA is not going to do work just as it is here. It's actually, we can make it a bit easier if we break it up into its component. So FA X component. So the work done by the force of A, or the force applied, and specifically its X component, plus the work done by friction is going to equal half the mass and then Vf squared minus Vi squared. So to work out the X component, it's going to be the force applied times cos of theta. So force applied is 80 times cos theta. And then remember, because we want to work out the work done, work is equal to the force times delta x times cos, and I'm going to call it beta here because I don't want to mix up the theta values. So we've done F, we need to do times delta x. So times delta x is 2, and then times cos of 0 degrees. And y is 0 because the object is moving to the left and the force is acting to the left. Then plus the friction is 8, delta x is 2, and cos of 180. Because friction is acting to the right, whereas the object is moving to the left. And that's going to equal half, the mass is 7, the Vi is 0, so it's simply going to be Vf squared, so 1.5 squared. Now we can simplify a bit. We're going to get 160 cos theta minus 16 is going to equal, this is 7.875. We can then simplify. We'll get 160 cos theta is going to equal 23.875. Cos theta is therefore equal to 0.149. Theta is equal to arc cos of 0.149, which is 81.42 degrees. Question 5.4. The angle between the applied force of 80 and the horizontal is now decreased. What effect will this have on the work done by the same applied force? So to answer this, I'm going to refer to a cos graph. A cos graph looks like this. Now, if we have an angle of 81, 81 is somewhere here. If I decrease the angle, say I decrease it there, the value of cos theta is going to increase. So if I decrease the angle, cos theta gets larger. If cos theta gets larger, that's going to mean that FA, X component, is also going to get larger because FA isn't changing. And that means the work done by FA in the X component is going to increase. So the answer here is it increases. Question number 6. A bat flies away from a stationary bat watcher at a constant velocity. The bat constantly emits sound waves at a frequency of 875 Hertz. So I'm just going to make some notes. The watcher is stationary, so VL is 0, the frequency of the source, so Fs, is 875. The bat watcher hears a change in pitch as the bat moves away from her. So question 6.1, name the property of sound related to pitch, that is frequency. Question 6.2, give a reason why the watcher observes a change in the pitch. Well, that's because of the Doppler effect. And I suspect for 2 marks, they want you to define the Doppler effect. The next part tells us, shown below is the air pressure versus distance graph, which represents the sound waves detected by the bat watcher as the bat moves away from her with a constant velocity. The speed of sound in air is 340 meters per second. So V is 340. Use the graph to write down the wavelength of the detective waves. So 6.3. In this diagram, I can see 2.5 waves. So here's one wave. Then here's another wave. That's 2, and then half. So 2.5 waves have a distance or a length of 1 meter. Wavelength is how long is one wave. So one wave is going to equal 1 divided by 2.5, which is equal to 0.4 meters. Now, question 6.4.1, determine the frequency of the sound waves detected by the bat watcher. So I can use the formula V is equal to F times lambda. 340 is equal to F times 0.4. F is thus equal to 850 Hertz. Now this is FL, the frequency that was detected by the watcher. Question 6.4.2, determine the velocity at which the bat flies. So if you look at the amount of information that we have that, and that. Calculating the velocity of the bat is not going to be that difficult. So we're going to go to our formula. FL is equal to V plus minus VL over V plus minus VS times Fs. Now, since it's moving away, you're going to have a small top and a big bottom. So in other words, you're going to have a minus in the numerator and a plus in the denominator. So 850 is equal to 340 minus 0, so just leave it as 340, divided by 340 plus Vs, which is what we want, times 875. We can then divide. We'll get 34 over 35 is equal to 340 over 340 plus Vs. We can then switch and then solve. You can get Vs is equal to 10 meters per second, and this is away from the listener. Let's move on now to question 7. Diagram below shows 2 identical spheres R and S placed on an insulated stand. The spheres carry charges of plus 9 microcoulombs and minus 5 microcoulombs respectively. They brought into contact and placed 30 centimeters apart. 7.1, calculate the charge on each sphere after contact. 7.1, Q nu is going to equal Q1 plus Q2 over 2. So 9 minus 5 over 2, which is, so that's 4. 4 divided by 2 is 2, so 2 microcoulombs. Question 7.2, draw the resultant electric field pattern. So positive charge, they are not going to overlap. And just make sure that we draw the same number of lines and the arrows pointing away from each other. Question 7.3, so after R and S have been in contact, a third sphere with a charge of 1 microcoulomb is placed between them. Okay, as shown in the diagram. Calculate the net electrostatic force. So I'm going to draw the forces that's acting on T. So T is going to be pushed to the right because of R. So it's going to be the force of R. And also T is going to be pushed to the left because of S. So I'm going to choose right as positive. So F net is going to equal the force of R minus the force of S. So the force of R is going to be KQ1 Q2 over R squared. So 9 times 10 to the 9 times 1 times 10 to the negative 6. Then 2 times 10 to the negative 6 over, they are 0.1 meters apart, so squared. And then for the other one, it's going to be 9 times 10 to the 9. Then 1 times 10 to the negative 6. Then 2 times 10 to the negative 6. And divided by 0.2 squared. That's going to give us 1.8 minus 0.45, which is equal to 1.35 newtons. Since it's positive, it's to the right. Question 7.5. Calculate the net electric field at T. So E net is going to equal F net divided by Q. So F net was 1.35. Q, or in other words, the charge of T, is 1 times 10 to the negative 6. So that's going to give us an answer of 1.35 times 10 to the 6 Newton coulombs to the right. Let's take a look at question number 8. The circuit diagram below shows a battery with an EMF of 12 volts, an unknown internal resistance. The resistance of the ammeters and connecting wires can be ignored, and the resistance of the voltmeter is very high. Question 8.1, write down the reading on the voltmeter V1 when the switch is opened. Now, it may not look like it, but V1 is actually connected across the terminals of the battery. So if the switch is open, the reading on the terminals across the battery is going to be the EMF. So it's going to read 12 volts. And you can test this by drawing lines from the terminals, and you'll see that it's going to connect straight to the voltmeter. Question 8.2.1. The switch is closed. The reading on the voltmeter V2 is 6. Determine the reading on ammeter A1. So 8.2.1, current I is going to equal V over R. So the voltage is 6, the resistance is 8. So that's 0.75 amperes. And that's going to be the reading on A1 because it's connected, they are in series, right? The current has not split between these points. Question 8.2.2, calculate the effective resistance of the parallel resistors. R parallel is going to equal product over sum, so 12 times 14 divided by 12 plus 14, and that's going to give us 6.46 ohms. Question 8.2.3, determine the internal resistance of the battery. EMF is equal to I into big R plus small r. 12 is equal to 0.75 into, the total resistance is going to be 8 plus the parallel, which is 6.46, so 14.46 plus R. We're going to solve for R. R is going to equal 1.54 ohms. Question 8.2.4, determine the reading on ammeter A2. So A2 is reading the current that is going through this resistor here. So what we can do is we can divide the current or the total current in a ratio. So I want to divide the 0.75 in a ratio 12 to 14. So to do this, you add them up. So 12 plus 14 is 26. And now, because 12 is smaller than 14, more current is going to go through the 12 ohm resistor than the 14 ohm. So the current is going to be 0.75 times 14 over 26. And that's going to equal 0.40 amperes. Question 8.3. The cost of electricity is 2 Rand 64 per kilowatt hour. A 3500 watt electrical oven is used for 50 minutes. Calculate the cost. So cost is equal to the rate times the time times the power. So the rate we are being charged is 2 Rand 65. The time must be in hours, so 50 divided by 60, and the power must be in kilowatts, so 3.5. And that gives us an answer of 7 Rand 73 cents. Question number 9. A simplified representation of a DC motor is shown in the diagram below. The current in the coil is in the direction X to Y. Name the component that ensures that the coil rotates continuously in one direction. That's going to be a split ring commutator. Question 9.2, in which direction will the coil rotate? So here you got to use your left hand. Okay, so your index finger is pointing in the direction of the magnetic field, so this way. Your middle finger is pointing in the direction of the current, so current is going away from us, and that means our thumb is going to point down. So this is the magnetic field, this is the current, that means our thumb is pointing down. That means that this part is going to point down, or is going to move down, and that part is going to move up. So it's moving in this direction. That is an anti-clockwise direction. Question 9.3. Write down the energy conversion takes place in a motor. It's electrical to mechanical because we have a battery. Question 9.4.1. An AC generator producing a maximum voltage of 311.12 volts is connected to an electric heater of resistance 30 ohms. Calculate the root mean square or RMS value of the voltage. So V RMS is going to equal V max, so 311.12 divided by the square root 2. And that's going to equal 219.995 volts. Question 9.4.2. Calculate the RMS current. Now, since we know the resistance and we know the voltage, we can say that I RMS is going to equal V RMS divided by R. So 219.995 divided by the resistance 30, and that's going to give us 7.33 amperes. Lastly, question number 10. The graph below represents the maximum kinetic energy of an electron, Ek max, ejected from the surface of a metal as the frequency f of light shone on it is increased. Question 10.2, write down the threshold frequency of the metal. So what we're looking for is the x-intercept. So we need to figure out what is this value right here. So we can see that the intervals going from 6 to 8, so that's 2. And if you count the number of lines and you divide it by 2, it means that each block is going to be 0.4. So if you count, you're going to go 1, 2, 3. So it's going to be 6 plus 3 into 0.4. That's going to give you 7.2. So the answer here is 7.2 times 10 to the 14 hertz. And that is our threshold frequency. Question 10.3. Determine the value of x indicated in the graph. So they want to know what is the Ek max when the frequency is 10 times 10 to the 14. So E is equal to W naught plus Ek max. So HF, and you can take W naught over, minus H times F naught is equal to Ek max. Now H is common, so let's take that out. So H into the frequency is 10 times 10 to the 14 minus the threshold frequency 7.2 times 10 to the 14 is equal to Ek max. Now all you got to do is substitute the H value in and we solve for Ek max. Ek max is going to equal 1.86 times 10 to the negative 19 joules. Question 10.4. The intensity of the incident light is increased without changing the frequency. How will this affect the kinetic energy? It's not going to affect the kinetic energy. It's going to remain the same. Because the only thing that affects kinetic energy is frequency. Only frequency affects EK. And that's the whole paper. Let me know how you did. If you stuck around right till the end, please leave a thumbs up. Don't forget to like, share, and subscribe for more. I'll see you in the next one.